All right, so let's get back where we left off with the rules of integration. And so we started out with one of the more commonly used rules, which is the so-called power rule for antiderivatives. So what's happening here is that we're taking the derivative of x raised to some constant power n. It's a very simple rule. The final result is going to be x to the n plus 1 power over n plus 1. And of course, don't forget the c. But the basic rule, remember, with derivatives and antiderivatives, everything works in reverse. So I've reminded you up here on the top how the power rule works for derivatives. And so you notice here, we're actually subtracting 1 from the exponent, but down here with an integral or antiderivative, you're actually adding 1 to the exponent. Now, if you notice down here, there's a little bit of a warning message here. Make sure that this is not the case for n equals -1. In other words, the integral of x to the -1 power requires a different rule, because otherwise we'd end up with division by 0. Okay, we'll get to that very quickly. So here's a simple example. The integral of x to the 4th dx, based on the power rule that we just learned, is x to the 5th power over 5 plus c. And we double checked it last time we looked at this one, and we saw that if you take the derivative of that result, x to the 5th over 5 plus c, you will in fact get back to x to the 4th. Also, don't forget the derivative of a constant is just 0. So when you take the derivative here, it just drops out. Here, this one's a little bit trickier just because you've got a negative exponent, but the rule doesn't change. In other words, your exponent here will be -2 plus 1 over -2 plus 1. So this reduces to x to the -1 over -1. Or we could write it more simply as -1 over x plus c. Okay, so every time we run into an integral like this, where it's just x raised to some power, then we use the exact same procedure. Now, the integral of a constant is even simpler. The integral of any constant k gives us back kx plus c. And the logic behind that is right here, because even though this says k, you can write this as kx to the 0 power, because of course, x to the 0 power is just 1. And so, of course, using the power rule, that would leave us with x to the n plus 1 over n plus 1 plus c. And if x had a 0 exponent in the first place, that means you'll end up with x to the 1 over 1, which is just x. And so that's what we have here. But because of this constant, we end up not with x, but kx. Okay, so in other words, whenever there's a constant involved, what you're effectively doing is you're multiplying k by the final result of applying a rule. And by the way, it's often common practice when we have constants, you can actually move them outside of the integral sign to make it a little easier to notice or determine what rule you're supposed to be using. Sometimes the constants can make things a little bit harder to figure out. So it's often the best job to just get them out of the way, move them outside, and then when you see what's left over on the inside the integral, it'll be easier for you to identify which rule you're supposed to use. So here we end up with 3 integral dx, which leaves us with 3x plus c. All right, now we're ready for some more complicated ones. Now, this is the case that I told you about earlier. The power rule, remember, applies for every case except an exponent of -1. So a quick reminder. Okay, and now this is that case, because this is actually integral x to the -1 power. And wait a minute, sorry, -1. This is the case where n is -1. So that means we can't use the traditional power rule. It turns out then that in this case, we end up with a natural log of the absolute value of x plus c. So this is that special case that I mentioned earlier. The power rule works every time except when n equals -1. When n does equal -1, as it does here, this is what we end up with instead. Now, this one is particularly simple. The integral of e to the x dx is just e to the x plus the constant. Wow, those are nice and easy. So let's take a look at a couple of simple examples. For example, this one. And again, you notice there's this constant here. We can just move it outside. And then you'll recognize right away, oh, this is that special case. The integral of 1 over x dx is the log of absolute x plus c. And I just realized I left out the c here. Oh, let me make a note to myself that this needs to be fixed. So this is 4C slide 421, yeah. So I keep saying, don't forget the C, and I did it myself. Yes, so don't forget that C. Okay, and also don't forget the 4. So in other words, it's true that the integral of 1 over x dx is log x plus c, but we still have this 4. So what you're basically doing then is you're multiplying all of this by 4. That's how you end up with 4 log absolute value of x plus c. And then, in a similar case here, I'm basically moving the 5 outside, and you remember from before, integral of e to the x dx is e to the x plus c. So that's what this is equal to. But because that 5 is there, I end up with 5e to the x plus c. All right, now the trig integrals. Yes, we can take integrals of trig functions. And if you look in the back of the book, you'll see there's a huge chart there for all these trig functions. Actually, they're all listed at the bottom. Let me get the book open and just show some of them to you. You might want to look at it once in a while because it really does have, it's a very valuable resource to have them all listed right in front of you. So, all right, hold on, let me find it. Oh, I should memorize what page it's on so I don't have to go through this every time. Here it is, part A, table of integrals 769. Now, if you notice with these online PDFs, 769 in the table of contents does not translate necessarily into 769 in the PDF document itself. It's close, but it's not exactly the same. So we have to keep scrolling. Oh, here it is. So you'll see that, yeah, there's some trig integrals here. And so the ones we're looking at here are the sine and the cosine. The integral of the sine of u du is negative cosine u plus x, c rather, and the integral of cosine u du is the sine of u plus c. So those are two that you'll see quite often. You might want to memorize them just for your own convenience because you'll see them so often. So here we go. Yeah, so by definition, the integral of sine x is negative cosine x. By the way, why is this? Let's just think about this for a minute. You might remember from earlier in the book, the derivative of sine x is the cosine of x. The derivative of the cosine of x is this negative sine of x. Remember, these integrals are antiderivatives. You're just essentially reversing what we're doing with derivatives. So if I took the integral, let's say of negative sine x, it would just bring me right back to cosine of x. Okay, because if the derivative of the cosine is the negative sine, the integral of the negative sine is the cosine. But here we have the positive sign. So that implies that our result will not be the positive cosine of x, but the negative cosine of x. Now this one is easier because if you notice, the derivative of the sine of x is the cosine of x, which means if we work that backwards and we take the integral or antiderivative of cosine of x, it should bring us back to sine x, and that's exactly what it does. So that's why these relationships hold. They're basically, like I said, you're when you take an integral like this, you're essentially reversing the process of differentiation. Now, there's a bunch of them. It starts to get very complicated very quickly. But again, if you look at this chart, you'll see a lot of them are already listed here for your convenience. Here's secant squared, for example, that equals the tangent. And you can probably guess why, because you might recall that the derivative of a tangent is the secant squared. And if you forgot, well, now you remember. So therefore, it makes sense that if I integrate the secant of x, it'll bring me back to the tangent of x. And then now some of these others are starting to look very complicated. But if you go back to the table, by the way, there should be also a table of derivatives in here too. It's probably table B. Look at some of these. Ooh, we won't be getting to any of these anytime soon. Yeah, here we go. Like, for example, the derivative of the cosecant is negative cosecant times cotangent. And then the derivative of the cosecant, sorry, the cotangent is equal to negative cosecant squared x. Oh, here's the one that we needed. I still didn't find it yet. The derivative of the secant of x. That's what we need for this last one. There we go. It's secant x tangent x. Okay, so that's why these last two look the way they do. In other words, the derivative, if you notice, of the cosecant is the negative cosecant times the cotangent. Here it's the positive cosecant cotangent. So this must become the negative cosecant. And then finally, the derivative of the secant is the secant times the tangent, which means that the integral of the secant times the tangent must give us the secant of x. Now, luckily with these trig functions, almost without fail, there are ways we can simplify these. There's actually quite a few simplifications that we can do with trig functions. We're not going to get into that just now, but sometimes when these things get really out of hand, it's often the case that we can find identities that'll help simplify our results. All right. Anyway, so here's an interesting example. Now, if you notice, this is a sum. We haven't seen this yet. Turns out, as you could probably guess, I can just rewrite that as the sum of these integrals. And often it is helpful for us to do this. So in other words, this is a tricky one to integrate the way it's written, but it turns out that each of these is not very difficult at all to integrate. So breaking it up into a sum of two pieces is the way to go. Now, we've already seen how to handle these. The x, this one, we will obtain it with the power rule. And this one, well, it's this rule. I don't know if there's a name for it. By the way, even though I just want to point out, even if you're now doing two separate integrals, you don't need to take into account the constant for both of these, because what will happen is you're just combining them anyway into this new constant. So you don't have to, like for example, here, this is e to the x, this is x squared over 2. You can combine these and then at the very end add the constant of integration. Okay, just to keep things simple, because you can gather up all the constants you want, but you're still going to wind up with a constant. And since we don't know what its value is, we can just add one at the end, and that's enough. So just in general, remember the notation we've been using is that capital F of x is the antiderivative or integral of f of x, the original function. And the same thing is true with the g's. So you can see that the integral of the sum is equal to the sum of the integrals. The integral of the difference is the difference of the integrals. And then here, I just moved the constant on the outside. And this, of course, is the integral of just this part. So these rules are very, very straightforward. There's nothing surprising here. Let's put it that way. And often, when you have a relatively messy expression, like I said, it's often your best approach to take it and break it up into as many smaller, simpler component parts as you can, so that it's obvious which rule you're supposed to use in each case. Often with integration, based on this table, you can see there's a lot of different rules you might potentially need to do integration. So rather than trying to tackle an enormous one all at once, most likely your best bet is to take whatever integral you have and break it up into smaller pieces, where each one individually can be handled much more simply. Like here's an example. You've got the integral, wow, you've got 4 terms. So you've got 5x cubed minus 7x squared plus 3x plus 4. And now each of these individually is very straightforward to integrate. You can apply the power rule to all 4 of these and you'll have your answer. So while it started out as a fairly complicated integral, by breaking it up into these pieces, you can see that it isn't really that complicated at all. And so let's see what our final result is. Now, like I recommended before, it moves the constants on the outside in each of these cases. And so it's even more noticeable, like here, for example, we're going to use the power rule to come up with x to the 4th over 4. This one will become x cubed over 3. This is x squared over 2. And this is just x. Now, don't forget about these constants, though. Okay, so there's here, actually, what I probably should have done is this. This one is 5 times x to the 4th over 4 minus 7, x cubed over 3 plus 3, x squared over 2 plus 4x. So that way you can see how we got from here to here. We have to make sure that we applied the power rule correctly, and then we multiplied by whatever constant we had. So these are the final results. And then, of course, at the very end, we can add our constant. Don't forget the constant, okay? But you only have to add it at the very end. You don't need it for each of these individual integrals. You can save that for the end. Oh my God, look at this one. Now, often when you see radicals like that, you're probably going to be better off rewriting it. For example, the square root is clearly x to the 1/2 power. Oops. the cube root is x to the 1/3 power, et cetera, because then it's easier to apply the power rule. Okay, so that's what I've done here. Now, there's one interesting change here. We've got this x here in the denominator. Luckily, all these terms are a function of x. So what you could do, say, well, you know what? This is x squared over x dx plus 4 x to the 1/3 over x dx. So the first term is just x. The second term, it's actually x to the minus 2/3 power, because what you're actually doing here, let me try that again. X to the 1/3 over x. Now remember, x has an implicit exponent of 1. You don't normally see it, but it is there. You've got x to the 1/3 minus 1. X to the minus 2/3. That means the second integral is 4 integral x to the minus 2/3 dx. All right, so that's what I have in the next slide. And so that's where we are now. Although this 4 ideally should be on the outside. But anyway, based on the power rule, this first one gives us x squared over 2. This one okay, so minus 2/3 plus 1 means that what you've actually got here is 4 times x to the 1/3 over 1/3. Okay, and that's what you're seeing here. Okay, you've got the x squared over 2, but dividing by 1/3 is the same as multiplying by 3. So you actually have x squared over 2 plus 12x to the 1/3, and then there's your c at the end. Okay, so we did this first. This is the result of the 2 individual integrals, and then at the end we can add the c. All right, so that was 4D in a nutshell. I mean, that was meant to be a brief introduction to some of the more commonly used rules of integration. Especially, I mean, these are really among the most important ones. But in the next chapter, we're going to be looking at more complicated cases, as you can probably imagine. So let's take a look and see what's coming up. By the way, I believe, as far as I know, I mean, for the rest of the course, we'll just be doing integration and applications of it. Because it is a very deep topic. Uh-oh, what happened? Oh, what happened? I want to make sure. I always am so concerned that I'm going to lose my work. Okay, we're good. But what I was trying to do, I always save these as both PowerPoint and PDF, because if you are using a Mac, there's a very real chance that some of what I'm writing on these slides will not translate onto the Mac. So at least with the PDF, it's guaranteed that you'll be able to see what I'm doing. If you're using a PC, it shouldn't be a problem. But if you're using a Mac, in particular, the symbols and the equations may not turn out correctly. The handwriting usually is fine, but I find that the equations and symbols can sometimes get mangled on a Mac. So, but the PDF is actually a picture of what we're doing. So you'll be able to see it properly on both platforms. Anyway, so now finally, in chapter 5, we're going to be formally introduced to integration. And what does it mean? What is it for? Well, actually, ultimately, integration is a way of calculating areas. That's ultimately what it's all about, calculating areas. So imagine you have some function or other, and you're interested in calculating the area under this function or this curve down to the horizontal axis, but only between A and B. We don't care what happens anywhere else. This is some real world function, let's say, where maybe this is the cost of production for some product or other, but we're only able to make products within the range A to B. So that means the rest of the X's are not relevant to us. So we're only interested in that area there. So if you notice, we're using the integration notation, but all of a sudden, we've done something different. You've got a range of specific values. This A and B are two constants. So what this means is that there's actually two types of integrals that we may encounter. This one is called an indefinite integral. And this one is called a definite integral. So far, all the cases we looked at were cases of the indefinite integral. What that means is you're actually taking the integral over the entire domain of the function. But if for some reason we don't need that, we only need the integral over a given range of values, then we'll use instead what we're going to call a definite integral. Okay, so that's the difference between the two. Now, so far, we haven't seen the procedure that we need to evaluate a definite integral, but we will get to that very soon. So it's important to be aware that there's two basic types of integrals that we might run across. The indefinite one, which applies to the entire domain, and the definite integral, which only applies over the interval A to B, including the A and the B. Okay, now, with that being said, that integral between A and B is actually equal to the area under the curve. That shaded region is the numerical value of this integral. So in other words, it has a specific meaning here. It is the area under the curve between those 2 points. So now by the way, we're going to take a little bit of a detour here. We're going to be looking at the summation operator. Sometimes it's called the sigma or summation notation. And we've seen this before. This is what I mean. This is the Greek letter sigma. Specifically, it's the uppercase sigma. And you might recall that this is the lowercase sigma. If you've had a statistics class, you know that that's used to represent the population standard deviation. But this is the summation operator. And we normally show an index. The I here is the index. It ranges from 1 to n. So this is simply shorthand. Oh boy, hold on one second. Every so often, the tablet gets a little cranky with me, and I have to reset it. All right, I think it's okay. So we interpret this as x1 plus x2 plus x3 plus up to xn. Now, here's a quick example of something like this. We have a set of temperatures observed in Minnesota during the first 5 days of January. So imagine yourself during Christmas break, you have family in Minnesota, so you decide to spend the week with them. And the first 5 days, you start to think twice because those are the temperatures. So if we needed to know the sum of those temperatures for some reason, we could use the summation operator to represent that. And in this particular case, there's 5 elements. And so we're adding up x1, x2, x3, x4, and x5. All right. Now, I just want to point out that the summation operator is a lot more general than what you're seeing here. We can use it to indicate a lot more complicated scenarios. Let me show you a couple of simple cases. For example, here, this now tells me that what I'm doing is I'm actually squaring the x's before I add them up. So using that same data I had before. And before, remember, we just simply added them up. Now we want the sum of the squares. So you'll have 2 squared plus -1 squared plus 3 squared plus 5 squared plus 1 squared. And that turns out to be 40 instead of 10. So you never know when you might need a function of x. And the summation operator can be very easily set up to show you exactly what you're doing. It's a very flexible operator. Let's put it that way. And now let's see a similar but not identical case. Oh, wait a minute. What happened here? These parentheses are there to tell us that what we've done is we've summed the numbers first, and then we squared afterwards. So I'm adding up my 5 numbers. So they look the same. They're very similar, but they're not. Add those up. I get 10 like I did before, but now I square the result and I end up with 100. Okay. And now one more. And I've chosen the ones that you're most likely to run into, but there can potentially be quite a few others, but we'll start with these basic ones. Now, this is a little unusual because you notice there's this k here. This k is some constant. And so what I have to do here is I have to run through all my x's. In each case, I'm subtracting the same constant. And then I square the difference. And when I'm done, I add them up. So this is a multi-part process. Subtract k from each x. Square the difference. And then add them up. So using the same data we had earlier, let's just say that the constant is 3. So this is x1 minus k, x2 minus k, x3 minus k. This is x4 minus k. And this is x5 minus k. We're squaring them all up, then we're adding them up. And you can see we finally end up with 25. All right. So that's really just, the tip of the iceberg for all the things we can do with the summation operator. But these are some of the more important ones. Now, it turns out that there's several important algebraic properties of the summation operator that we need to know. So, for example, what if I'm adding up a bunch of constants? Well, that's a very strange idea. So here I've got a constant c, which I'm adding to itself n times. And so naturally enough, I end up with nc. Let me show you an example of that. What if the constant is 3 and n is 5? Right, so let me just quickly remind you what the rule is. Okay, so the sum of all the c's is nc. So here, c is 3 and n is 5. So I'm just adding up 3 5 times. So of course it stands to reason that I end up with 5 times 3, which is 15, or n times c. All right, well, that was easy. Now, what about a case like this? We have something like what we've seen up to this point. The sum of this constant c times xi, I can move the c outside. So whatever this sum is, I can then multiply the sum by c rather than doing it for each term. And I think you'll agree this will save me a lot of time, especially if this is a large data set. There's no point in multiplying each x by c and adding them up when you can just add all the x's and then multiply by c. So this is a very convenient property. Let's say, for example, we go back to Minnesota and look at the temperature data, and I want to know the sum 2xi. So, I mean, I could double them all, or what I could do is just say, well, I already know that this is 10. So I end up with 20. It doesn't matter which one you use, but I think that by moving the constant on the outside, I think you'll find that it's quicker. All right, now, some more algebraic properties. These, of course, are just what you would expect. The sum of these terms, the sum of the a's plus bi's, can be rewritten as the sum of the a's plus the sum of the b's. And the same thing is true with subtraction. Okay. So, the thing is, you'll use the one that is the most convenient. In many cases, it really doesn't make any difference, but sometimes breaking this up into smaller pieces can actually help simplify a problem that we're working on. And sometimes it doesn't make any real difference. So you always want to choose the one that's the most convenient, but you need to know that these are both correct. Now, here's one that might be surprising at first glance, and then you'll realize, wait a minute, no, this looks perfectly sensible. What's going to happen here is that we're going to take a sum and break it up into 2 parts. So let's say we have something like this. Now look at these carefully. I equals 1 to n of the AI. We know what this means. What I can do is break it up into 2 parts. I here goes from 1 to m, and then here from m plus 1 up to n. So why don't we do an example here? Using the data that we've been using, 2, -1, 3, 5, and 1. We've already seen that this equals 10, but what I can do here is write it like this. In other words, it's just, this one would just be 2 plus minus 1, and this would be 3 plus 5 plus 1, and I'll still end up with 10. Now, again, you're probably wondering, why would you ever do this? Well, what might happen is that you might have values that some are negative and some are positive, and this means you can split them up and treat them separately from each other. That's a possibility, but it's just, again, it's important to know that you're able to do this. And of course, there's nothing to stop you from breaking this up into 3 or 4 or 5 pieces, as many as you need. Okay, and also, of course, it's understood that this applies to subtraction as well. Now, here's some interesting results. This is something you might not have encountered before. Some of these summation formulas can be reduced to an algebraic formula, let's say. You'll see what I mean in a second. It turns out that the sum of the indexes from 1 to n, which means, as you can see, it's literally just 1 plus 2 plus 3 plus 4 plus ... plus n. It turns out this can be simplified to n plus 1 over 2. So why don't we try one? Suppose we're interested in this one, where the n is 5. Let me write that as 5. Okay, so what do we have here? 15. So since n is 5, is it true that n plus 1 over 2 is 15? 5 times 6 over 2, what do you know? It's 15. So now this can come in very handy if you have a very complex sum of some kind, where there's multiple components. And in fact, this is also another motivation for taking an existing sum and splitting it up into smaller pieces, because some of those smaller pieces may have helpful formulas like this that we can take advantage of. Oh, there's a lot of them. We're just going to see a few of the most important ones, but there's quite a few. But, they involve often very complicated ones. Now, I squared is a little bit messier. Right, let's take a look at this one. Ooh, that's starting to get very complicated. So let's prove it. Or at least show it with one example. We're not going to actually prove it. That will come in later classes. So what is that? 5, 14, 30, 55. All right, and so since n is 5, let's see how that works out. Well, it works well. Okay. Interesting. So again, if you have a very messy expression and you split it up into individual terms, and one of them happens to be the sum of the I squares, then you can easily calculate this without having to actually go through and add them all up, square them and add them up. So in other words, this can save you an enormous amount of time. Now, I cubed is even more messy, as you can guess. So again, we'll look at the first 5 numbers. All right, what does that add up to? Um, 225. So let's confirm that 5 squared times 6 squared over 4. What do you know? It's 225. Because 25 times 36 is 900. When you divide that by 4, you get 225. So far we have I squared, and I cubed. Are there any others? Oh, there's a bunch of, but now here's, oh, I like this one. We're going to take this scary looking expression, I minus 3 squared. So I minus 3 squared can and should be broken down. Actually, no, let's do this with FOIL. I squared minus 3I minus 3I plus 9. So, oh, and it says it right here anyway. I squared minus 6I plus 9. Now, based on the rules we had earlier, I can rewrite this as I squared, sum of I squared minus sum 6I plus sum of 9. Now, I can also write it like this. This one, I guess you can just leave it like this because it's a constant. And we already know how to deal with all three of these. Okay, so on the next slide, they're broken out properly. So this is a quick reminder that I squared equals n plus 1, 2n plus 1 over 6. So because we're going from 1 to 200, we have 200 times 201 times 401 over 6, which leaves us with 2,686,700. Now for the next one, you might recall that the sum of the i's, just the sum of the i's, not squared, is n plus 1 over 2. But because the 6 is here, negative 6, we'll end up with what did I do? No, sorry, this is I, just plain I. So whatever that turns out to be, that is the value of the second sum. So we see that on the next slide. And again, because n is 200, we've got minus 120,000. And of course, remember how this works. So we have, in this case, we have 9n. 9 is the constant. And we have 1,800. So that means that we bring them together. And this is, so we copy them from the last few slides, and this is our final result. So basically what this did was it not only reminded us how these rules work, but it showed us why we wouldn't just leave it like this. I mean, can you imagine? You'd have to, I don't know, maybe there is a formula floating around out there that we could have used, but I think it's easier to just break it up into the simplest possible components. Now, I don't think the book has a chart of these summations. They're in the book, but I don't think there's a separate table where we can look them up. It's possible that there's a table on the internet somewhere, but I'm not sure how you would even look for it. What would you call these? I'll tell you, let's see. Maybe it would be something as simple as summation formulas. You never know what you might find out there. See, now there's two of them. Ooh, I think maybe we're in the right track here. Oh yeah, I mean they're really tiny, but there they are. If only, yeah, if only they were bigger. But yeah, there here they are. There's quite a few interesting ones. Oh, okay. Here they are. They're bigger here. Like they've got I to the fourth, which we didn't go over. 2i. Oh, well, these are applications. Anyway, so there they are if you're looking for them. All right. Now here's another one. Now look at this thing. Oh, this one isn't hard at all because it's just the difference between two exponents of I. Okay. And we've already seen how both of these work, so this won't be a problem. And so let's start with I cubed. Actually, we've got them both. We've got I squared and I cubed. I cubed is n squared, n plus 1 squared over 4. Since n is 6, we have 6 squared times 7 squared over 4. 36 times 49 over 4, or 441. Up here, we have I squared, n plus 1, 2n plus 1 over 6. I is 6, so 6, 7, 13 over 6, 91. So we're going to look at the difference between the two, and that gives us 350. Now, you're probably wondering why we went through all of that. Well, you'll see, because it turns out that while certainly an integral is or can be interpreted as the area under a curve, the integration itself, the actual operation itself, can also be interpreted as an infinite sum. And so that's why this is so important. And you'll see what that means as we get to that point. But what we're actually doing when we take an integral is literally adding up an infinite number of areas under a curve to come up with the final result. It's literally an infinite sum. So we have to understand the properties of sums. Now we're going to see here a derivation of how to find the area under this curve between the two endpoints A and B. Now, if this was a square, we'd be all set, of course, but we don't know, there isn't a specific formula here. So what we're going to end up doing is this. We're going to create a series of rectangles. To represent the area under this curve. Now, you can see the way I'm drawing it, the approximation isn't really that great, is it? No. Not yet. My drawing isn't that great either. So yeah, now here's the thing though. Now each of these rectangles, and we'll see this as we go further into the chapter, has the same width. Which we'll call delta x. But they all have a different height. The height of each rectangle and that's taken from the function. The function will tell us how tall each of these rectangles is. So remember the area of a rectangle, if you've forgotten, is the width times the height. So in this diagram, you can see I have all these rectangles. I'm going to calculate all their areas and add them up. Now you can see the two that this is going to give me only a rough approximation to the area under that curve. So with integration, what we're actually going to do is shrink up those delta x's so that we have more and more rectangles. And in the limit, when the number of rectangles goes to infinity, the delta x's are converging to 0. And when we reach that point, the sums of all these rectangles will exactly give us the area under that curve. And so integration is the sum of an infinite number of rectangles. That's what it is. So anyway, we'll get more deeply into that. I think maybe we'll have to save that for next time because this is a very complex discussion. So anyway, I guess we'll stop right here. We've covered quite a bit of ground. And next time when we pick it up, we'll be looking more deeply into what integration actually means. And then we'll get back to our calculations. All right, so I'll see you all next time.